A parametric equation is a group of functions that depend on the same parameters. So in 2 dimensions, the point here is represented by x and y, and any point on the curve can be obtained in the closed interval AB by changing this single parameter t. So for example, if t equals a, then we have x and y at a. And we can find the derivative, or the slope of the tangent to the curve, at a point by differentiation using the chain rule. So the derivative, or the slope of the tangent to the curve, is dy dx, which using the chain rule is dy dt by dt dx, which is the same thing as dividing dy dt with dx dt. And the derivative is defined if the derivative of x with respect to t is not equal to 0. Let's find an anti-clockwise parametrization for a semicircle with a radius of 2. Well, a parametrization defines every single point on that curve using a single parameter. So if we look at a point on this curve, then we can visualize that our parameter t is the angle. So we can define the x-coordinate as the radius cosine t, and the y-coordinate can also be defined using trigonometry as 2 sine t, where t is between 0 and pi for the semicircle. So for t equals 0, x is 2 and y is 0, and for t equals pi, we can see that x is equal to negative 2 and y is equal to 0. So therefore this is indeed an anti-clockwise parametrization. Given this parametrization for a semicircular curve, find the slope of the tangent to the curve at t equals pi on 4. Well, that's the derivative dy dx, which is equal to dy dt by dt dx using the chain rule, or dy dt on dx dt. So dy dt is 2 cosine t, and dx dt is minus 2 sine t. So the 2's cancel, and at t equals pi on 4, this evaluates to 1 on root 2 on minus 1 on root 2, which is minus 1. So where the angle is pi on 4, or 45 degrees, the slope of the tangent to this curve looks something like this, and that makes sense. We can obtain a second derivative for a parametric curve in a similar way that we obtained the first derivative using the chain rule. So if we set the first derivative as y dash, then the second derivative of y with respect to x is equal to the derivative of y dash with respect to the parameter t multiplied by dt dx. So dy dash dt is basically the derivative of the first derivative with respect to the parameter t. And therefore, this can be written as dy dash dt over dx dt. And the second derivative tells us whether a point on a parametric curve is an inflection point, or whether the curve is concave up and concave down at that particular point. Given these parametric equations, derive an expression for the second derivative. So recall that the first derivative dy dx is equal to dy dt on dx dt. So that gives minus cosine t on sine t. And following a similar trend using the chain rule, the second derivative is dy dash dt on dx dt. So using the quotient rule, we have minus sine squared t minus cosine squared t over sine squared t. And then dividing through by dx dt, which is minus 2 sine t, that's going to give you minus a half cosec cubed t. Let's find the arc length of this parametric curve in the closed interval from a to b, and noting any point in this interval on this continuous parametric curve can be described by x and y, where x and y are functions of the parameter t, and the parameter t is in AB. So designating the length along the curve as delta s, and the horizontal and vertical dimensions, so we can write the following relationship using Pythagoras' theorem. And on the right hand side, we can divide by delta t squared and multiply by delta t squared, which doesn't alter the expression. And now we can factor out delta t squared and take the square root of both sides, and in the limit as delta t approaches 0, and if we integrate both sides with this equation, along the length of the curve on the left hand side, and on the right hand side we integrate with respect to the parameter t. And this gives us the length of the parametric curve between a and b, or the distance that a particle travels along the curve. Let's show that the circumference of a circle is 2 pi r using the following parametrization. Well, using the arc length integral, where t is between 0 and 2 pi for a circle. So we integrate from 0 to 2 pi, and dx dt is minus r sine t, and squaring that gives r squared sine squared t, and dy dt is r cosine t, so squaring that gives r squared cosine squared t. And now if you factor out r squared and use a trig identity, you get the following integral. And now evaluating this integral, you'll get this result. Scalar valued functions take a scalar as an input and output a scalar. So in this example, the point here is described by two scalar functions. Now in contrast, a vector valued function takes a scalar as an input and outputs a vector. And here is an example of a special type of vector known as the position vector, which is measured from the origin, and that vector gives the location of that point. So what we do is add the horizontal dimension, which is x, and x equals f of t, and we multiply this by the unit vector I, which gives the direction along the x-axis. So I has a magnitude or length of 1. And similarly in the vertical direction, we multiply the y-coordinate of the point, which is given by g of t, by the unit vector in the vertical direction. And you can observe this visually over here. So effectively drawing the position vector along the curve in this interval effectively traces out that curve. We can extend the methods for differentiating real or scalar valued functions to vector valued functions. So suppose we have the vector valued function that takes an input t, and that gives the following position vector. Well, similarly, we can write r at t plus delta t as follows. And using vector addition, we can obtain a relationship between r at t plus delta t and r of t, where delta r is the secant vector between 2 points along the curve. And rearranging this equation and dividing through by delta t, and now if we take the limit from both sides, as delta t approaches 0, we get the derivative of r with respect to t. And I encourage you to make these substitutions and use the rules for limits, and you'll be able to write the derivative as follows. And now if you differentiate this first derivative, you'd obtain a second derivative in the following form. And note that when we differentiate, the position vectors I and j do not change magnitude or direction, so they just remain constant. Let's plot the curve traced out by this vector valued function. So x of t is equal to t, and y of t is equal to 1 minus t squared. So what we'll get are the following values from t equals minus 1 to 2. And now we can draw vectors from the origin to these points. So the first point is at minus 1, 0, 0, 1, 1, 0, and 2 minus 3. So basically our curve is going to look something like this. So we plotted the curve described by this vector valued function in a previous video, which is a parabola, from t equals minus 1 to 2. And now we're asked to find the tangent to the curve described by the following vector valued function when t equals 1. So if we differentiate this vector valued function, we obtain the horizontal unit vector minus 2t by the vertical unit vector. And when t equals 1, we obtain I minus 2j. So as we can see, when t equals 1, we're looking at the point 1, 0. So the tangent vector is going to look something like this. So for every 1 unit in the horizontal direction, the vector goes down 2 units in the vertical direction. So in other words, the slope is minus 2, which makes sense. Given the same vector valued function we plotted previously, we now want to verify that the point xy, when t equals 0, is a minimum. So if we differentiate this vector valued function, we'd obtain a horizontal unit vector minus 2t by the vertical unit vector. And if we differentiate again, the second derivative of r with respect to t is going to give you minus 2 by the vertical unit vector. So when t equals 0, which is described by this point at 0, 1, we can see that the tangent vector described by the derivative is in the horizontal direction, and the vector of the second derivative points downwards at this point. So because this vector points downwards, then this point is not a minimum, it's actually a maximum. Given the vector valued function that we plotted earlier, let's determine an equivalent real valued function y of x. Well, as we can see, x of t is equal to t, and y of t is equal to 1 minus t squared. So therefore we can write y as a function of x by substituting for t. So that's effectively 1 minus x squared, and that gives the equation of this same parabola over here. We can extend the methods for integrating real valued functions to parametric or vector valued functions. Now suppose we have the instantaneous rate of change of position with respect to time. So in this case that represents the velocity, but this can be any rate function. So what we do first is separate the variables, where the derivatives are written in shorthand notation, and now we can integrate both sides. So we can take the unit direction vectors outside the integral, because they're constant, and use the addition rule to break this up into two integrals. And then once you evaluate these integrals, you're going to get the position is equal to some function plus a constant of integration for the horizontal direction, then plus the y component of the position in the vertical direction. And now you can apply your given initial condition and evaluate those constants of integration. And we'll do that in an example problem. Given the following vector valued rate function, find an equation for r if we have the following initial condition. So if we separate the variables and integrate both sides of the equation, then we obtain the following result, where cx and cy are the constants of integration. And now applying our initial condition, then what we obtain for the component of this vector in the horizontal direction is 3 is equal to 1/3 by e to the power of 3 by 0 plus the constant of integration. And in the vertical direction, we obtain pi on 4 is equal to minus cosine of 0, which is 1, plus the constant of integration. And now you can solve for the constants of integration, substitute them back into this equation, and you found your equation for r. We can describe the motion of a particle moving along a planar curve using parametric or vector valued functions. And given we're looking at motion problems, the parameter t represents time. So the velocity is obtained by differentiating the position vector with respect to time. And differentiating the velocity with respect to time is the same as obtaining the second derivative of position with respect to time, and that gives us the acceleration. Now if we integrate the velocity vector with respect to time between time t0 and time t, well that gives you the displacement or the change in position over that interval of time. And from this you can solve for the position. So recall that the instantaneous speed is the magnitude of the instantaneous velocity, which is written as follows. And if you integrate this with respect to time from time t0 to time t, well that gives you the total distance the particle has travelled, or the length of the curve from time t0 to time t. And you can recognize this as the arc length integral. Given a position vector for a projectile with this parabolic trajectory, derive an equation for the velocity and acceleration. So in this context, the parameter t is time, because we're looking at a motion problem. And differentiating the position with respect to time, we obtain the velocity, and differentiating the velocity with respect to time, we obtain the acceleration. So basically the acceleration is constant, so only the gravitational acceleration is acting downwards at any point, and it has the same magnitude and direction according to this equation. Now for the velocity, the horizontal component is also constant, and at the top of the trajectory, it's going to look something like this. And given that the acceleration is pointing downwards, then this point is a maximum in the trajectory. And then somewhere over here, the velocity is going to look something like this, but the horizontal component always has the same magnitude, in accordance with this equation. Given the acceleration vector for a projectile, derive an equation for the velocity and position. So the acceleration is the rate of change of the velocity with respect to time, and that's equal minus the gravitational constant in the vertical direction. And now we can separate the variables and integrate both sides while leaving the constants outside the integral. What we get is the velocity vector is equal to some constant in the horizontal direction plus minus g by time and plus another constant of integration in the vertical direction. And now applying our initial conditions, so equating the horizontal components and the vertical components at time 0, well what we get is g by 0 plus cy. And therefore the equation for the velocity can be written as follows. And now you can do the same thing to obtain an equation for the position. So the velocity is the rate of change of position with respect to time, and separating the variables and integrating, and applying your initial condition, you'll be able to get an equation for the position as a function of time. The following function describes the motion of a particle along a curve, and we're asked to describe the motion by analyzing the velocity and acceleration vectors at several points along the curve. So differentiating the position with respect to time, we get the velocity. So we can see that this is a parameterization of a circle with a radius of 1. So substituting for t is 0, we get the velocity pointing in a vertical direction. And drawing in the velocity vectors by plugging in the relevant values for t, they look something like this at these points. And now the acceleration can be obtained by differentiating the velocity with respect to time, and plugging in those different values for t, you're going to get the acceleration vectors all pointing to the center. So we call this acceleration as a centripetal acceleration, or center-seeking acceleration that keeps the particle traveling along a circular path. We've represented points in Cartesian coordinates using x and y, while in polar coordinates, we'll represent the same point using r and theta. So in polar coordinates, there's a pole, and a polar axis extends from it, and this polar axis has a magnitude or length of r to the point we're looking at. And the angle of the polar axis to the horizontal axis is theta. So we can relate the polar coordinates to the Cartesian coordinates using trigonometry. So the x coordinate is r cosine theta, and the y coordinate is r sine theta. And also using trigonometry, we can observe that tan theta is y on x, which is sine theta on cosine theta. And we can also observe that as we move to different points in the plane, the Cartesian unit vectors have the same magnitude and the same direction, whereas the unit vectors in polar coordinates have a constant magnitude but can have a different direction as we move to different points in the plane. Polar curves are special types of curves where r is a function of theta. And here are some examples of polar curves. So the first one in yellow is a cardioid, or a heart-shaped curve, which is defined by the following function. So this defines every point on the curve in polar coordinates. And if we look at the circle with the radius of r, well, that's defined by r is equal to r, because r is always constant no matter what the angle is. And this half line here is defined by theta equals alpha, because the angle of this line is constant and doesn't change. And for the vertical line through x equals b, if we draw some line from the pole to a point on this line, well, this line r at some angle theta from the horizontal axis is constrained by the following equation. So r cosine theta is always equal to b for every point on this line. You can turn this around and write r is equal to b on cosine theta. So as you can imagine, if theta is equal to pi on 2, then this polar function is not defined. Given a curve defined by the following polar function, and given the relationships between Cartesian and polar coordinates, we can extend the methods for calculating the derivatives of real-valued functions to functions in polar coordinates. So dy dx gives the slope of the tangent to the curve at some point along the curve. And using the chain rule, we can take the derivative of y with respect to theta and multiply by the theta dx. So note that r is a function of theta, and therefore this can be written as follows. Now designating this as y dash, we can obtain a second derivative of y with respect to x. So this can be visualized as follows, which is the same thing as dy dash dx. So therefore we first differentiate y dash with respect to theta and multiply by the theta dx. So therefore this can be written as follows. And in the following examples, we'll see how these derivatives give information on a curve that's defined by a polar equation. Let's plot the polar curve defined by the following equation. So you may recognize this as a cardioid or a heart-shaped polar curve because these two values are equal. And here we can see that cosine theta is equal to cosine of minus theta. So basically by your cast rule, you can see that cos is positive in the first and fourth quadrants. So this curve is going to be symmetric about the x-axis. So we just need to plot half the curve above the x-axis and then reflect it. So for a few angles, if we take an angle theta equals 0, so what we have is 2 plus 2, which is 4. So that's our first point on the curve. And if we take theta equals pi on 2, well, cosine pi on 2 is 0, so we get r equals 2. So that's our second point on the curve. And if we take theta equals pi, so that would give 2 minus 2, which is 0. So connecting these points together using a smooth curve, so the curve's going to look something like this. And what you do is just reflect this about the x-axis, because as we saw it's symmetric. So this is our final curve. Let's plot the following polar curve. So you may recognize this as a limacon with an inner loop because this value is less than this one. And because cosine theta is equal to cosine minus theta, the curve is symmetric about the x-axis. So we need to plot the top half of the curve. So choosing a few angles, so theta equals 0 gives r is equal to 3, so that's 1 point on the curve. Theta is equal to pi on 2 gives r equals 1, so that's our other point. And now when theta equals pi, r equals minus 1. So we have 1 minus, so our third point's actually here. And joining these points by a smooth curve, you get the following curve. And I'll leave it for you to verify why this curve passes through the origin by using your special trig angles and their supplementary angles. And because the curve's symmetric, we can just simply reflect it about the x-axis. So it's going to look something like this ultimately. Let's plot this polar curve. Well, given that 2 is greater than 1, then this is going to be a limacon with a dimple. And given sine theta is equal to sine pi minus theta, well, we have symmetry about the vertical axes. So therefore, we can plot one half of the curve to the right of y and reflect it about the y-axis. So now starting with an angle of 0, r is equal to 2. So that's our first point on the curve. And for theta equals pi on 2, r equals 3. So that's our next point on the curve. And because we have symmetry about the y-axis, we can choose theta is equal to minus pi on 2 or 3 pi on 2. So sine of minus pi on 2 is minus 1, then 2 minus 1 is 1 over here. So our curve looks something like this. And due to symmetry, we can reflect it about the y-axis. Let's plot the following polar curve, and because of the r squared term, you may recognize this as a lemniscate. And given that r squared is equal to minus r squared, so we're going to have symmetry about the origin. And now if we choose a few angles, theta equals 0, r squared is equal to 0, so therefore r is 0. And when theta is equal to pi on 4, sine pi on 2 is 1, and root 1 is 1. And when theta is equal to pi on 2, sine pi is 0, so we come back to this point. And what the curve looks like is something like this. And if you go beyond pi on 2, so for example, an angle of 3 pi on 4, then what you'll get is sine 3 pi on 2, which is negative 1, and then square root of negative 1 is not defined. So the lemniscate is not defined in this quadrant over here. And by symmetry, the other half of the lemniscate looks something like this. Let's find the derivative for the following polar curve. So remember that x is equal to r cosine theta, which can be written as follows using the double angle trig formula, and y is equal to r sine theta. And using the trig identity, we can simplify this as follows. And now we can evaluate dy dx. So that would be dy d theta over dx d theta. And if you substitute for theta equals pi on 2, which represents this point on the curve, you'll get a slope of the tangent to the curve of positive 2. So the slope of the tangent to the curve at this point looks something like this, which makes sense. Let's derive an equation for the second derivative of this polar curve. So x equals r cosine theta, and using trig identities, that's sine 2 theta. And y is equal to r sine theta, so using the double angle trig identity, we get 1 minus cosine 2 theta. And now the first derivative is equal to dy d theta on dx d theta, which is equal to tan 2 theta, and taking the second derivative, where the first derivative is y dash, so it's equal to dy dash d theta, which is 2 sec squared 2 theta, on dx d theta, which is 2 cosine 2 theta. And therefore that's equal to sec cubed 2 theta. We can extend the concept of calculating the area of a region bounded by a curve from rectangular coordinates to polar coordinates. Now suppose we have a polar curve where r is a function of theta, and if we define theta as the angle between the horizontal axes and our polar axes, and delta theta as the angle between these two lines that are very close. And therefore r multiplied by d theta gives us the arc length, delta s, or the length of the base of that triangle. And then 1/2 multiplied by the base, by the height of that triangle, is going to give us an approximation to the area of this triangular slice. And therefore in the limit, as delta theta approaches 0, then the area of the infinitesimally thin triangle can be written as follows. And now we can integrate both sides of this equation between some angle theta A to some angle theta B. And this gives us our final equation to calculate the area bounded by a polar curve between two angles. Let's calculate the area of the region bounded by this cardioid. Let's write out the area integral. So for this cardioid, we're integrating from theta equals 0 all the way around to theta equals 2 pi, and our radial function is 2 plus 2 cosine theta. And now we can expand and simplify this, and now you can use your double angle trig identity to simplify this term and evaluate the integral, and that's going to give you the area bounded by this cardioid. And post your answer in the comments. We can find the area of a region between two polar curves by extending the definite integral of finding the area of a region enclosed by one polar curve, which we derived as follows. So recall that we summed up the area of a bunch of triangular slices from some angle theta A to theta B. So let's just call this red curve, curve A, and if we apply the same definite integral to a second green curve, so the area enclosed by that curve can also be written using the same definite integral. So therefore if we subtract the area within the red curve from the area within the green curve, then we obtain the area of this region between those curves. So therefore our definite integral to find the area between two polar curves between angle theta A and theta B is written as follows. So typically you'd find these angles where the curves intersect, and you'll be able to evaluate the integral. Let's calculate the area of the region inside the limacon and outside the circle. So that would be this region over here. And recall that the area between curves is defined as follows. So if you substitute r equals 3 into this equation, then you can see that the curve intersects when cosine theta is 0. So therefore theta is a multiple of pi on 2. So these are the intersection points over here. So what we do is integrate from minus pi on 2 to pi on 2, and we're integrating radius of curve A squared minus the radius of curve B squared with respect to theta. And now you can expand and simplify this, apply your trig identities, and you'll be able to obtain the area. Let's calculate the area of the region bounded by the inner and outer loops of the limacon. So because we're looking at one polar curve, we're going to use the area integral for a single polar curve. So if we first integrate from theta equals 0 to theta equals 2 pi on 3, and we integrate r squared with respect to theta, well that's going to give us the area of this top half of the curve. And now if we subtract the area of this region by continuing to integrate from 2 pi on 3 to pi, and we integrate r squared with respect to theta, well that's the same thing as subtracting the area of this region due to symmetry. So what we've effectively done is obtain the area of this top half of the curve between the outer and inner loops of the limacon, and if we multiply this result by 2, well that's going to give us the area of the entire limacon between the outer and inner loops. So if this is not clear, post your questions in the comments. Let's calculate the area of the region inside the lemniscate and outside the circle between theta equals 0 and theta equals pi on 2. So what we're looking at is the first quadrant and this part of the curve. So we need the intersection point between the two curves, and we can do that by substituting r equals root 2 in this equation. So what we get is root 2 squared is 4 cosine 2 theta. So cosine 2 theta is equal to 1/2. And for this to be true in the first quadrant, then 2 theta is equal to pi on 3. And therefore theta is equal to pi on 6. So as we can see, the curves intersect when theta is 30 degrees. And now we can apply the area integral to obtain the area between those two polar curves. So we're integrating from theta equals 0 to pi on 6, and the radius of the outer curve squared is the lemniscate, so that's already squared, so we don't need to square it again. And then minus root 2 squared integrated with respect to theta. And that's going to give us the area of that region.